So, in this lecture we will learn about rapid mixing. So, the basic question that we want to know is something of this kind. So, assume that we have n cards. How many times do you have to shuffle so that the shuffle becomes something like a uniform sampling? How many steps are required to ensure that the shuffle or the arrangement of cards resembles a uniform sampling? It is a little bit vague question, we will make it more precise later on. Okay. So, if we draw what we want to really have is, let us imagine all the possible arrangements of cards. There are n factorial arrangements. When we sample after shuffling, how many times should we rearrange such that the arrangement at a particular time looks like one that is obtained by doing a uniform sampling from this n factorial arrangements. So, we will describe what our shuffle operation is. Okay. So, suppose we have a deck of cards. Okay. We pick one card and then put it on top. Okay. So, amongst these n cards we pick one at random, uniformly at random, and put it on the top. So, this is our shuffle operation. So, how many times do we have to do this shuffle operation so that the arrangement looks like the one obtained by uniform sampling? This is a question that we want to answer. So, we will introduce a notion of how close it is to uniform sampling. Okay. So, we will define something called as variation distance. Okay. So, let us imagine that D1 and D2 are distributions on a sample space. Okay. The variation distance between D1 and D2, okay, so that is written as D1 absolute value or D1 minus D2, okay, norm of D1 minus D2. This is defined as sum over all the elements of the sample space, the absolute value of D1 x minus D2 x, okay, this divided by 2. So, at each point in the sample space, compute for each point compute D1 x. D1 x is the probability that x is chosen if the underlying distribution was D1, and D2 x is the probability if the underlying distribution was D2. Look at their difference, take its absolute value, sum it up over all the points of the sample space and divide the sum by 2. What we get is called as variation distance. Okay, now, we will just relate this variation distance to some other quantity. Okay, so, if you look at D1 minus D2, the variation distance, this is equal to the maximum over all subsets of S of the sample space D1a minus D2a, its absolute value. Okay. So, look at all possible subsets of the sample space and look at the difference between the probabilities that these distributions assign to the set or the event A, that will be equal to the variation distance. The proof is very straightforward. So, let us look at all these points, and if you look at all points inside the sample space, there are some points, some collection where d1 x is greater than or equal to d2 x, which we will call as S plus, and the others are where d1x is less than d2x, that we will call as S minus. Okay. So, S plus is the subset consisting of all points where d1 x, so all points x where d1 x is greater than or equal to d2 x, and S minus is similarly the subset consisting of all points where d1 x is less than d2 x. Now, note that if you take the entire sample space, since this is a distribution, d1 s is equal to d2 s, and that this is equal to 1. Now, let us look at this quantity that we are interested in, max over all subsets d1 a minus d2 a. its absolute value. Clearly, if you take S plus, that will be the A which maximizes this quantity. So, if you take d1 a minus d2 a, this is maximized when A is S. So, this is equal to d1 S plus minus d2 S plus, and if you look at d2 a minus d1 a, and if you try to maximize that quantity, that is maximized when A becomes S minus. So, this is equal to d2 S minus minus d1 S minus, because S minus consists of all points where d2 dominates. So, on that subset d2 S minus minus d1 S minus will be maximized. Okay. If we look at d1 S plus plus d1 S minus, that is two disjoint parts of the sample space S. So, this is equal to d1 S and is equal to 1. Similarly, d2 S plus plus d2 S minus will be equal to d2 S, and that will also be equal to 1. So, max over all subsets, absolute value of d1 a minus d2 a, this is equal to both these quantities, and those quantities will essentially be equal. If we take this as equation 1 and equation 2, we subtract them, what we will get is d1 S plus minus d2 S plus plus minus of d2 S minus plus d1 S minus, and the right hand side both being equal to 1, they subtract out and gives 0. So, d1 S plus minus d2 S plus is equal to d1 S plus minus d2 S plus is equal to d2 S minus minus d1 S minus. So, these quantities are the same. So, therefore, d1 a minus d2 a is maximized at this point, and d2 a minus d1 a is maximized at S minus, and they are equal. So, the maximum of the absolute value is just d1 S plus minus d2 S plus plus d2 S minus minus d1 S minus, the whole divided by half. Now, if you take d1 S plus minus d2 S plus, this consists of one region which consists of all points where d1 is greater than d2, and the second portion is all those points where d2 is greater than d1. So, we can write this entire expression as sum over the absolute value of d1x minus d2x, where x belongs to S, and this into half. So, this is nothing but the variation distance. So, variation distance can also be seen as the maximum possible difference that can be there for the probabilities of events when you look at those events under distribution d1 and d2. Now that we understand what is variation distance, we will want to look at the number of steps. Okay, we need to define what is called as rapid mixing. We will do this by defining rapid mixing in terms of variation distance. Okay. So, let us say, so intuitively what rapid mixing means is the Markov chain quickly moves towards its stationary distribution. So, let us say pi is what we will call as the stationary distribution, and let p x t denote the distribution at time t on starting at x. Okay. So, let x be any point in the state space of the Markov chain, and let the Markov chain evolve for t seconds or t time steps. How close is it to the stationary distribution? If it approaches the stationary distribution quickly, then we will say it is a rapidly mixing Markov chain. So, we will define certain terms. So, let us say delta x t. Okay, so, this is the variation distance. So, this is a distribution, p x t is a distribution and pi is a distribution. So, let us look at the variation distance between p x t and pi. Okay. So, this we can think of as a difference between the distribution if you allow the Markov chain to start at state x and evolve it for t time units. Depending upon the value of x, this number could be different, and the maximum over all choices of x, delta x t, is what we will call as delta t. We will define some more quantities. So, tau x epsilon we will define as the time taken for the variation distance between p x t and pi to reach epsilon. Okay. So, if you had evolved this Markov chains by starting at x, how much time will it take before the variation distance becomes less than epsilon? So, that is denoted by tau x t, and the maximum value of tau x epsilon when x ranges over all possible states, this is defined as the mixing time. Okay. So, if the mixing time is small, what it means is for every state, if you begin a Markov chain at that particular state, the number of steps taken for the variation distance to be smaller than epsilon is at most this value. Okay. Suppose the mixing time is t, then in t steps we can guarantee that the variation distance between the distribution and the steady state distribution will be no more than epsilon. Okay. So, if tau x epsilon, the maximum or all x is called as tau x, and tau x is what we call as the mixing time. This tau x is small. We will later on describe as to what it means to say that the tau x is small, but when it is small, then the underlying chain is called as rapidly mixing. Okay. So, in a nutshell, what this means is we now have a definition for telling that a Markov chain mixes quickly. We want to know, or I mean, when we say that it mixes quickly, it means that it reaches its steady state distribution quickly. We want to know how can we prove that certain Markov chains are rapidly mixing. So, methods for proving rapid mixing. Okay, we will see one such method. The method is called as coupling. Okay. So, we will define what is a coupling. We will require another definition. So, let MT be a Markov chain and let this Markov chain be on some state space S. Now, let us take another Markov chain ZT, which consists of two parts. Okay. So, xt and yt. So, it consists of two processes xt and yt, and we say, so zt also we want it to be a Markov chain. And this zt is a Markov chain on the cross product space, on S cross S. Okay, we can think of many such Markov chains. For example, if you take a simple random walk on a graph, and if you take a copy of it and do these things together, then that can be something like zt. Okay. So, now when do we say that this is a coupling of the chain MT? Okay. So, if you look at the marginals, since zt consists of two parts xt and yt, if you look at the marginals, they should behave exactly like the Markov chain MT. In other words, probability that xt plus 1 is equal to x prime given zt is equal to x comma y. This probability should be same as probability that mt plus 1 is equal to x prime given mt is equal to x. And similarly, the other marginal also should behave similarly, that is yt plus 1 is equal to y bar given zt is equal to x y should be equal to the probability that mt plus 1 is equal to y bar given mt is equal to y. If these conditions are met, then we will say that this is a coupling. Okay, zt is a coupling of the Markov chain MT. So, one way to obtain coupling would be to take identical copies which are completely independent of each other, okay, but that is not the kind of coupling that we will be needing in order to prove rapid mixing. What we will look at is a coupling wherein these xt and yt, they are in their own rights Markov chain, but once they have a tendency, we will try to make couplings in such a way that this xt and yt has a tendency to move towards a common state, and once they reach the common state, they continue in that particular state. Okay. So, when they reach a common state, that is if xt is equal to x and yt equals x, okay, when such a situation has been reached, we will say that the chains have coupled. Okay. So, once again we first define what is a coupling. Coupling just means that the marginals should behave like the underlying Markov chain. Okay. We say that they are coupled if the individual Markov chains xt and yt have coalesced into a particular state, from there onwards they stay in that state. Even if they continue in the same state, we know that these equations will be satisfied, because both of them will have identical marginals. Okay. So, now we have seen what is coupling and what is a coupled Markov chain. Now, we will have a lemma called as coupling lemma, which is known as coupling lemma, and this is the key tool that we will use to show that certain Markov chains are rapidly mixing. While we were thinking about rapidly mixing, we mentioned that the Markov chains should quickly move to its stationary distribution, but we did not say what exactly is quickly. Okay. We will do that when we are looking at the examples of using coupling lemma. Okay. So, let us state coupling lemma. Suppose Zt is equal to Xt Yt is a coupling of some Markov chain Mt. If there exists a T such that probability that Xt not equal to Yt given x 0 is equal to x and y 0 equals y, if this is less than epsilon, then tau epsilon is less than or equal to t. Okay, let us see this lemma closely. So, what we have is we have a coupling of Markov chains. So, Xt and Yt are the marginals. Now, suppose somebody could guarantee that the probability that these do not become, these Xt and Yt, probability that they do not become equal is small, irrespective of the starting state. Okay. No matter which state you begin, the probability that Xt and Yt are different, if that probability is bounded by epsilon, that means that probability is at most epsilon, then the mixing time for parameter epsilon is going to be less than t. In other words, in time t they would have mixed to the extent of variation distance being no more than epsilon. Okay. We will see an application of this lemma. So, we will solve the card shuffling problem using this. Okay. So, in our card shuffling problem, we will think of a Markov chain in the following way. Okay. So, individual states are is one particular configuration of cards. Okay. So, the total sample space, the total state space of the Markov chain is of size n factorial. Each possible arrangement is one of the states, and from each state what we will do is, if the arrangement was let us say 1 to up to n, we choose one position at random and then put it on the top of the pile. Okay. So, at each node what we are doing is, whenever we are in a particular state, what we are doing is we will choose one of these cards at random and put it at the top of the pile, and we keep on doing this. So, this is the MT for us. Okay. The underlying Markov chain or the Markov process is MT, wherein the states are configurations, and from each state it goes to one of the neighboring states. So, you can note that the sample space is of the state space is of size n factorial, but from each node there are exactly n minus 1 transitions to make. We can also just redundantly say that when we are choosing one at random, we choose the first node also with equal probability, in which case we just stay in that state. So, we can say that there are at most or exactly n neighbors for each particular sample state in this state space. So, we have one such Markov chain, and what we will do in order to construct the coupling is the following. Xt is just a copy of mt, and yt is going to be, so yt is going to mimic the moves on xt. Okay. What does it mean to mimic the moves on xt? So, xt is basically moving from one particular configuration into another by choosing one particular card. Okay. So, the state at any time t is fully captured by the arrangement of the deck. Now, suppose we moved from xt to xt plus 1 by picking a card, say C. In yt, what we will do is, in yt move C to top to obtain yt plus 1. That means, if card number 10 was brought to the top to obtain the next state in xt, in yt also you just pick the card 10 wherever it is and put it on the top of the pile. Okay. So, of course, the starting configurations could be different for these two different chains, but xt and yt there is some kind of relationship between them. Okay. What is interesting is these chains have a tendency to move towards a configuration such that the states match, and if you have the states match, then from that point onwards they will remain in the particular config, they will have the subsequent states being equal. So, xt and yt have a tendency to match moves. Okay. What we need to know is how long will it take for xt and yt to be identical. Okay. And how do we use coupling lemma? So, coupling lemma states that if the probability that they do not match, if that is small after a particular time t, then the time t is going to be a bound on the mixing time. Okay. So, let us ask this question: how long will it be before x and y match? Okay. In other words, what we want to know is probability that xt equal to, or let us look at the complement event, not equal to it given x 0 equals x and y 0 equals y. Okay. We want this probability to be less than epsilon. Can we find a time t such that this statement is true? If we could find such a time, then we can use the coupling lemma and say that the mixing time for the variation distance to be smaller than epsilon, or mixing time for parameter epsilon, will surely be less than t. Okay. So, how good or how small a t can we find out? How much? So, xt and yt are to be different. Okay. So, when can we say that xt and yt are same? Xt and yt are same means their state space have coalesced. Okay. So, if we think of this entire thing as you are starting your random walk at some particular point x, and the other random process y will start at some particular small y, they will move around, this will also move around, and finally they will reach a point, and after that they will continue on the same path. Okay. We want to know how long will it take before this happens. Okay. Since the deck is completely characterized by the arrangement of cards, and we know that if some card, let us say if card 10 has ever been picked, their position in both cards will then always be same. Okay. So, this is some particular card. If card 10 was picked and it was brought to the top, then in the other deck also the card 10 would have been brought to the top. from wherever it was. So, once a card is picked, later on arrangements will not change the position of 10. That holds true for any other card that you pick. So, if every card has been picked once, then xt and yt would coalesce. Okay. So, that we will write it as a fact. If every card has been picked once, the Markov chains xt and yt would have coalesced. Okay. So, now what we need to tell is how long will it take for every card to be picked at least once. Okay, that is just coupon collector. Okay. So, let us say that we keep on picking the cards for n log n plus Cn steps, C we will choose later on. So, if we keep on simulating the Markov chains for n log n plus Cn steps, each step, every card has a probability of being picked. So, let us look at some particular card, let us say probability that card I is not picked in n log n plus Cn steps. Okay, that would mean it should not have been picked in the first step, not in the second, not in the third, and so on. So, 1 minus 1 by n is the probability of not being picked in the first step, and then it is not picked for n log n steps, that would be the product. So, 1 minus 1 by n whole raised to n log n plus Cn. Okay. So, this is going to be 1 minus 1 by n the whole raised to n times log n plus C. Okay. So, that is going to be less than 1 minus 1 by n raised to n, that is e raised to minus 1. Okay. So, this is e raised to log n into e raised to minus C. So, that is equal to e raised to minus C by e raised to log n is just 1 by e raised to minus log n is by n. Okay. So, a card I is not picked with probability e raised to minus C. So, probability that there exists a card which was not picked. Okay. So, this probability is going to be less than or equal to, we can apply union bound, there are n possibilities. So, that is going to be e raised to minus C. Okay. So, if we choose C to be say log 1 by epsilon, and probability that there exists a card which is not picked, or we will call that as a probability of the bad event, is going to be less than e raised to log 1 by epsilon and negative of this. So, that is going to be epsilon. Okay. So, probability of bad event is going to be epsilon. So, we can just write this as if t is equal to n log n plus n log 1 by epsilon, that is equal to n log n by epsilon, then the probability that x t not equal to I t given a starting configuration, that is going to be less than epsilon. Now, once we have this, we know that the mixing time is going to be less than n log n by epsilon. Okay. So, in n log n by epsilon time, the Markov chain that we had constructed will reach stationary, very close to stationary distribution, in the sense the variation distance between the distribution that has been reached and the stationary distribution is going to be less than epsilon. Okay. So, look at the Markov chain, it had n factorial states. okay, although it had n factorial states, in n log n by epsilon moves, the fraction of states that would have been explored is very small, okay, that is a tiny fraction. And if let us say epsilon is 1 by n square, okay, the number of states that has been explored is n log n cube, which is approximately 3 n log n, okay. So although you have only simulated the Markov chain for 3 n log n steps, the Markov chain is now equally likely to be in any one of the n factorial states, okay, almost equally likely. So since there are n factorial states, since the Markov chain is the one which we constructed is aperiodic and it has all the nice properties, we can argue that its steady state distribution is going to be the uniform distribution, okay. We could take epsilon to be much bigger than this, we could take epsilon to be let us say 1 by 2 raised to n, even then we are running it for only, so if epsilon is 1 by 2 raised to n, then n log n times 2 raised to n is going to be less than n square, but let us say certainly less than n cube. So even if you run the Markov chain for n cube steps, okay, we are going to get some distribution on the states which is very close to the uniform distribution. So 1 by n factorial minus 1 by 2 raised to n or something like that, okay. So we could have taken this to be larger than 1 by 2 raised to n is larger quantity than 1 by n factorial, but we could have taken this to be let us say n square, and even then we do not, there is not much harm done in the calculations, okay. So if epsilon is 1 by 10 n factorial, which is 2 raised to n log n, okay, then n log 2 raised to n log n is approximately n square, okay. So if we take this to be n cube, then we know that we get very close to the uniform distribution, okay. If we have taken n to be epsilon to be 1 by n square, that is not good enough, because this probability is significantly higher than 1 by n factorial, okay. Now we will see yet another application of this coupling method, wherein we will look at random walk on a hypercube. Okay. So a hypercube, as we had seen before, it is a graph, okay, let us say n dimensional hypercube, okay. It is a graph where every bit string of length n is present, okay. So these are the vertices, every n length bit string is a vertex, okay, and the neighbors are all those vertices which can be obtained from this by flipping one digit. So if you flip the ith digit, whatever you get, that is going to be one of the neighbors, and you can flip any of the n digits, okay. Now in this random walk, we will assume that we toss a coin, and if the coin is heads, we stay there itself, otherwise we will transition by choosing one random position to flip, okay. So xt plus 1 is equal to xt with probability half, and this is equal to say S, where S is obtained by a single bit flip of xt. So take xt and flip one bit, and that bit is chosen uniformly at random. So since there are n position, all of those things are happening with probability 1 by 2n, okay. So this is the random walk on the hypercube that we are interested in. Now what we want to know is how long will it be before we will get uniform distribution or almost uniform distribution on the hypercube. Okay. So, how long will we have to simulate the chain to reach the steady state? You can convince yourselves that there is only one stationary distribution for this, and it is the uniform distribution. Okay. So, in order to answer this question, we are interested in is we want to say if it is to be away from the uniform distribution by an amount epsilon, then how much time will it take? In other words, we want to find out the mixing time of this random walk. We can do a very similar thing as the previous example. So, again x t is going to be the same random walk. So, x t plus 1 or the random walk x t is empty and y t is obtained by mimicking the moves of x t. Okay. Mimicking the moves means if x t had changed the ith bit, then y t will also change the ith bit. Okay. So, we have to be careful if the ith position, if you look at a state that consists of a bit string, if the ith position was flipped from 0 to 1 in x t, and if y t was in a state where this is already 1, then you just do nothing. If it was 0, then you change it to 1. So, when you mimic, it essentially means that after the move both x t and y t will agree on the position where the change has been made. Note that if you look at these two Markov chains jointly, then you can see that the marginals will exactly be empty itself, because there was some probability of this bit flipping. If it was flipping, then it can flip to, it can either flip or stay with some probability, and the same thing happens in y t as well. Okay. So, x t and y t has the tendency to couple, and once they have coupled, it remains, the marginals anyway are same as empty, and once they have coupled, they remain in that particular state. So, what we want to know is probability that x t not equal to y t given some initial condition. So, whatever is the initial condition, if we have identified all the, I mean if we have chosen at random all the positions in the state space, that is, I mean you look at any state, each state will consist of n bits. If each of these bits were chosen even once, then the chains would have coalesced. So, we will just write this as a fact. If every bit position was chosen at least once, we can guarantee that x t would be equal to y t. Okay. So, that is, if every bit position was chosen at least once by time t, then we can guarantee that x t equals y t, and from there onwards they will remain same. Okay. So, now how do we upper bound the time taken for x t equals y t? Again it is the same as the previous analysis. Each of these positions had equal probability of being sampled. There is a factor half, which is with probability half you remain in the same stage itself, but if you ignore that part and if you just imagine this to be a chain which is running 2 times slower than the earlier one, we can say that this is similar to coupon collector problem. How much time will it take for you to collect n coupons, and that is again going to be something like n log n, and if you run the chain for n log n by e steps, n by epsilon steps, you can argue that all positions would have been chosen at least once. Okay. So, this concludes the week on Markov chains and the mixing properties of Markov chains. We will again see the mixing properties of Markov chains when we look at approximate counting.